You know when you're driving down the highway and you see one of those absolutely colossal storage tanks? Ever just stop and wonder, how in the world does that much steel hold back millions of gallons of liquid without just bursting? It's a fantastic puzzle of pressure, materials, and some seriously clever engineering. Okay, so let's really get into it. For any engineer designing one of these beasts, the number one question is this: how thick exactly does that steel need to be? You have to calculate it perfectly. Because if you get it wrong, the consequences are, well, they're catastrophic. But if you get it right, that tank will stand for decades.
So how do we actually solve this thing? Well, we're going to peel back the layers of the onion. We'll start with the core problem itself. Then we'll identify the main force we're really fighting against, turn that physics into a working formula, see how engineers tweak it for the real world, and finally, we'll uncover a really cool secret that makes it all work.
All right, let's start at square one, the core problem. Before we can even think about doing any math, we have to know exactly what kind of tank we're building. And it turns out there's a very specific rulebook for that. And that rulebook is called API 650. It basically sets the stage for us. We're talking about vertical cylindrical tanks that are sitting fully supported on a foundation. And even though they're called atmospheric tanks, they can handle a little bit of pressure, about 2.5 psi, and temperatures up to about 93 Celsius. These specs right here, they define our entire engineering challenge. Okay, so we know what our tank looks like. Now, what's the main force we're actually fighting against here? It's time to identify the real culprit. You see, a tank like this has a lot trying to knock it down. You've got wind pushing on it, earthquakes trying to shake it apart, not to mention its own incredible weight. But when it comes to deciding the thickness of that steel wall, one force is the absolute king, dwarfing everything else: the static head, which is just a fancy name for the hydrostatic pressure of all that liquid inside. So what exactly is static head? Well, it's actually pretty simple. It's just the pressure that a column of fluid creates by its own weight when it's just sitting there. The taller the column of liquid above any single point, the more pressure you have at that point. It's that direct. And this is where the real challenge comes in. That pressure isn't the same everywhere inside the tank. It's practically zero right at the surface of the liquid. But as you go down, it increases and increases and increases until it's at its absolute maximum right at the very bottom. This creates what engineers call a triangular load on the tank wall.
That triangular load is everything. So now, let's make the jump from the physics concept to an actual formula. Let's build the fundamental equation that engineers use to fight back against that pressure.
Okay, let's build this together, step by step. Step one, we calculate the pressure at any given depth. The formula for that is P equals rho GH. That's just the liquid's density times gravity times the height of the liquid above our point. Simple enough. Step two, that pressure is constantly pushing outwards, trying to burst the tank. This creates a tension in the steel wall that we call hoop stress, and the formula for that is pressure times diameter divided by 2 times the thickness. And finally, step 3. We just do a little algebra, flip that equation around to solve for the one thing we really need, the thickness, T. So thickness equals pressure times diameter divided by 2 times the allowable stress. Now, this is a classic, beautiful formula. It comes from something called thin shell theory, and is the perfect place to start. But, and this is a huge but, the real world is always a bit messy, so engineers have to add a few crucial adjustments to make this formula truly work in practice. So how do we deal with all that real-world messiness? Well, that brings us to the next step, real-world adjustments, where we bridge that gap between a clean theory and a practical, working design code. First off, we can't let the stress in the steel get anywhere close to its breaking point, not even close. So we use something called an allowable stress. But here's where API 650 gets really clever. It actually gives us 2 different limits. There's the normal design allowable stress for everyday long-term operation, but then there's a higher test allowable stress that's only allowed during the one-time water fill test, where you can safely push things just a little bit further. Now, here's something really wild that engineers don't have to worry about as much with these tanks. You'd normally think that a welded joint would be a weak spot, right? But the API 650 code has this almost magical rule. It basically says if you follow our specific welding and inspection rules, you can just assume that joint is 100% as strong as the steel plate it's connecting. That's a huge simplification that makes life so much easier. And the last key adjustment is that we have to plan for the future. So we add what's called a corrosion allowance. It's literally just a little bit of extra steel thickness added to our calculation. This acts as a safety buffer, making sure the tank is still safe even after years and years of potential corrosion.
Okay, so let's put all those pieces together. It's time to reveal the engineer's secret. We're about to see the final formula and the brilliant little trick that's hidden right inside it. So after all that, this is the formula that engineers actually pull from the API 650 code. It should look pretty familiar, right? You've got the diameter D, the liquid's specific gravity G, and the allowable stress SD. But wait a minute. Look really closely at the height term. See that? It's not just H, it's H minus 0.3. And that should set off some alarm bells in your head. Hold on a second. Why on earth would we be subtracting 0.3 meters from the height? We just spent all this time establishing that the pressure is the absolute highest at the very bottom. Shouldn't we be using the full height to be as safe as possible? What is going on here?
The answer has a fancy name. It's called discontinuity stress. But the idea is actually pretty intuitive. Our simple hoop stress formula is perfect for the smooth, curved wall of the tank. But where that flexible wall meets the rigid flat floor, you have a sharp corner. That sudden change in stiffness, that discontinuity, creates all sorts of complex, localized stresses that our simple formula just can't predict.
And this, right here, is the engineer's secret weapon, the 1-foot rule. The code basically acknowledges that our simple formula breaks down right at that stiff corner joint. So through decades of experience, they found a brilliant workaround. They said, let's just calculate the thickness at a point 1 foot, that's our 0.3 meters, above the bottom. At that point, the formula works perfectly again. So you use that calculated thickness for the entire bottom ring of the tank. It's an elegant, practical, and safe solution to a super complex problem.
But they don't just do this calculation once and call it a day. Oh no. A tank is built in rings, or courses, stacked on top of each other. So for that bottom course, you calculate the thickness using the height measured 1 foot from the very bottom. Then for the second course, you do the calculation again, but this time you measure from 1 foot above the bottom of that course, and you just keep repeating this all the way to the top. And the result of that whole iterative process is actually beautiful. You end up with a tapered shell. The bottom course is the thickest because it's holding back the most pressure, and then each course above it gets just a little bit thinner. It's an incredibly efficient design that saves a massive amount of steel, weight, and money.
So let's just recap the whole journey real quick. The core principle is that the static head is what determines the shell thickness. The mathematical foundation is that classic hoop stress formula, PD/2T. But the secret sauce, the practical magic that makes it all work safely in the real world, is that clever 1-foot rule, which takes care of all those tricky stresses at the joints. And that leaves us with one final thought to chew on. This 1-foot rule is fantastic, and it works for tanks up to about 61 meters in diameter. But what about the really giant tanks? The ones where saving just 2 millimeters of steel means saving tons of weight and a whole lot of money. For those, how do you think engineers get even more precise to optimize the design even further?